Welcome back. We were discussing about the space data protocol and the modification of TCP for that. So, for that what we have found out that in the space system the loss of packet can be due to many reasons, at least 3 reasons identified, which is corruption, that is noise, the link outage and congestion. So, we were talking about the corruption induced loss, and in that said how it is handled. First, the onset of the corruption is to be identified, which is identified by the link layer, and the link layer is passed on the information to the higher layer, that it says that it has a CRC error, but it can be demultiplexed, it can be still used. So, receiver runs a moving average and sets a threshold. From that threshold, once it exceeds the threshold, it says that corruption is experienced. So, it declares that when the threshold is crossed, and the receiver goes into the link corrupted state. So, it changes the state. So, link corrupted state, the receiver starts sending corruption is experienced, a separate type of message, which is a internet control message. It sends to the destination that I have experienced. It sends the data and also it sends the corruption experienced, and the destination in response informs the source of the TCP that the link is corrupted. The acknowledgement is going, along with that it says that I am told that link is corrupted. Link is corrupted, that is the important information for the sender. It does not go into the slow start mode as normal TCP assumes that this is a congestion. It knows that it is corrupted. So, destination TCP remain in the state for 2 times RTT unless the state changes, the state change message has come that it is not corrupted, etc. So, that is the response. Destination TCP waits simply that there is a corruption, a little bit of corruption, it simply waits, and the response sending TCP does not reduce the congestion window. It does not reduce the congestion window and does not back off its RTO, RTO timeout back off, which is normal TCP's algorithm. It does not do that. So, it does not do the congestion control. That is what is important. It simply waits, and then when the acknowledgement is received without corruption experienced, there is a very small corruption was there. After that, corruption experienced is that information is not there in the acknowledgement, then it is says that the corruption state is come out. So, TCP starts working normally, sender starts working normally on that. So, it is pictorially shown, taken from a reference, that is as the link is corrupted in the downlink. In this case, the receiving ground station, the local cache, they detect it, and it along with the data it says that there is a internet control message packet, that is corruption experienced. A special message is sent, and that is sent back along with the ACK, the receiver, that is the destination sending to the source that corruption is experienced. Is the additional information which is going in the loss due to corruption. Let us see other possibility. Link outage. Link outage is a transient phenomenon. Link outage is a transient phenomenon. For a short duration it may come when the satellite goes out of visibility of the station due to any object, it comes under the shadow of object, or because of any other reason, or some short term outage due to loss of synchronization due to heavy rain, etc. I was just mentioning earlier. There may be many reasons. So, link outage is handled also in similar 4 phases as we discussed in corruption case. So, first is the identification, and the physical layer again can identify this. Link outage means no signal is coming. So, signal strength has gone below a threshold and synchronization is lost. So, once that is done, it sends a signal, that is link outage message sent to the local host. It is not corruption experienced, it is called link outage message, a slightly different message is sent to the local host or the destination, because link is out. So, in the forward side towards the destination, it can send that message, and the response of that is a TCP source enters in the persist mode and send occasional probe packet. It just it just stop transmission, it just sends sometimes after some time a probing packet that link has come back or not. And it suspends all timers and sees normal retransmissions, etc., what is supposed to happen. It does not send anything, it does not transmit, does not retransmit, but only occasional packet, probe packet it transmits. And when terminates, that when link is restored message is received from the physical layer, that this phase is terminated, that is the link outage phase. The link restored information is available from the physical layer, that is modulator, demodulator will get into sync, and that message can be sent to the higher layer. So, it can be pictorially shown, that is there is a satellite has gone into the shadow of the receive station, and there is a temporary link outage which is detected here because the signal is not coming, and so there are special control message packets are sent to the destination that link is not there. So, it cannot do anything. When the TCP source goes into persist mode, it does not get ACK, so it goes into persist mode, and it occasionally send probe packet. So, when the probe packet is through, then signal is again detected, and then this will come out of the destination, and normal thing is restored. So, it does not go into slow start mode. That's very important, because this is a transient phenomena. The satellite is moving, and it will go out of the shadow of this object, and the link will be restored. So therefore, it does not go into the congestion experienced and slow start mode, that is the link outage. But then in satellite network there also can be congestion, like normal network, it is there. When it exceeds the network capacity, it is congestion. So, in that case also there are slight modification of the protocol. We need not go into very detail, but just briefly I will try to mention. In a space link, it is expensive to recover from the losses due to long delay and limited power. That is important. It has limited power and it is a long delay. So, therefore, it's quite expensive to recover. So, there is a variation of the normal standard TCP, which is called TCP Vegas. We need not go into very much detail of that. Briefly I will mention some of the important characteristics of that. The TCP Vegas variation of the slow start algorithm is used in the space environment. Now, what it does, that it doubles the CWND every second RTT, every alternate RTT instead of every RTT. It goes up slowly there. That is part of the TCP Vegas, it is a standard thing. And congestion avoidance phase is entered by measuring the throughput, reduction of the throughput. Throughput increase, and normally throughput go on increasing. So, when it tapers, then it understands, instead of earlier standard TCP, that is it exceeds CWND exceeds the SS threshold, that is what is the congestion avoidance phase. In this case, the throughput is tapering. So, CWND equals the bandwidth delay product of the network. It tries to maintain always, and then in congestion avoidance phase, continuously it measures the achieved throughput and it adjusts the CWND accordingly. We are not going to detail how it is adjusted. Those who are interested, they can read that RFCs, corresponding RFCs and the standards which are available from the Internet Task Force. Congestion control is invoked by sending host in response to a loss when RTO expires and when the explicit congestion notification is received from the destination host. This is also existing in the standard TCP. So, there is a special notification when the layer the in between routers they understand that there is a congestion is happening, they try to send this notification to the destination saying that congestion this congestion is expected. So, destination host accordingly. So, the congestion control is invoked based on these two issues, and then there is a source quench notification received from the intermediate router. This mechanism is received faster than ECN from the destination and is preferred in a long delay link. The difference I will just try to mention, that in between router when it understands that there is a congestion is going to happen, ECN it sends to the destination, and then destination will send in its acknowledgement that congestion ECN has come. So, sender will take certain action. That is a longer process, and if this router sends source quench notification sends back to the sender, then this mechanism is received faster than ECN. Then in a long delay link it is advantageous. So, satellite data links normally carry heavy traffic in one direction. So, that is about congestion thing and different types of error sources detection and corresponding mitigation technique what we talked. Now, we are getting into the another issue in the satellite channel, which is asymmetric channel. Satellite data links are normally carry heavy traffic in one direction, and other direction carry normally ACKs, like say a large volume of data is monitored, and say a radar data or moon surface data is collected, which is a high volume data is sent in one direction. The other direction will only ACK. So, other direction carry only ACK. Now, ACK is very small amount, it is only header. So, this reverse link is normally put along with the telemetry and telecommand, which is a very low bandwidth link. So, in one side the heavy volume of data is coming, other side the ACK is going, which goes along with telemetry telecommand link, which is we have seen earlier, is already 10 kilobits per second, that type of link, low bandwidth. In case of large data file transmission, the reverse link may overrun with ACK, because large files are coming with segment side. So, each segment will be sending ACK. So, now the ACK will be more than telemetry telecommand. So, this may overrun. So, that could be a problem. So, reduce large amount of ACK transmission. We have to reduce that. All packets that are not ACKed, all packets are not ACKed. Instead, only nth packet is ACKed. So, it is got some sort of a delayed ACK mechanism. So, I reduce the volume of ACK to accommodate them in the reverse link, which is telemetry telecommand link, which is a low bandwidth. This is managed. This is how it is managed in the asymmetric channel in the space link. Let's see the other thing, which is link capacity. It's a limited link capacity. We know the power available at the satellite probe is limited. So, accordingly, to get the proper C by N, the link capacity, the bandwidth has to be reduced. Satellite channels are power limited and have relatively less bandwidth compared to the terrestrial channel. We know this. So, here since bandwidth is less, bit efficiency is very important. We should not send the bits which are not relevant or not important for that particular link. So, now you see TCP had a header of 20 bytes, normal header, it is not extended header, 20 bytes for small data. When the data volume is small compared to the header is much larger, then channel capacity is unnecessarily absorbed or consumed by the header itself, and all the 20 bytes may not be useful. So, two mechanisms are proposed in this to improve the performance. This is specifically for the space data link. One is called header compression, and another is called selective negative acknowledgement. Okay. Let us look at these two techniques briefly. Header compression. Now, there is a standard header compression which is available in the TCP, which is actually some sort of a delta function, that is whatever earlier header was there and the new header, the difference of these two. It's very simple, but that is the standard. But in this case, they are not doing that. The satellite based TCP header compression is different than the conventional TCP header compression, which is also available as standard, that is based on differential header transmission. It is not that. There are problems. So, we need not discuss into so many details. What is proposed, that is what we will discuss. Satellite based header compression summarizes the static information and omits the information that is not relevant for the present connection. I briefly just mentioned, that is, instead of source address and destination address, which are quite long in terms of, they give certain identifier, port identifier. So, source port and destination port address are very long, so many bits are there. So, instead they use unique some port identifier for each fragmented each segments, as long as the connection is there, that port identifier identifies clearly. So, that could be much smaller in length, unique identifier, or in the like TCP flags, there all flags may not be used. So, those things can be. So, the static informations which are not dynamically changing during the connection, that can be reduced. So, this way about 50% of the header compression can be achieved. So, this is the technique which is slightly away from the standard header compression proposed by IETF, that is Internet Engineering Task Force. It is slightly different than that, but it is much more reliable. It has been found, experimented and proposed and accepted by the CCSDS, and roughly about 50% header compression they have achieved. The other technique is selective NAC, SNAC. Now, SNAC is not in the standard TCP protocol. In the TCP protocol, there is a NAC, only NAC, but which is not used as a standard, but which is already proposed, and selective ACK, which is already existing and proposed as well as taken as a standard TCP. So, this is slightly different than these two. This is specially used only for space environment TCP. There is a negative acknowledgement, and this is negative acknowledgement and request for retransmission. Normally, if you remember, the TCP says acknowledgement, which is positive acknowledgement, and if you do not get a positive acknowledgement within certain time, then you retransmit. So, not receive of positive acknowledgement is treated as a loss of data. In this case, receiver says that, clearly says that this is not received. So, it is a negative acknowledgement. So, there is a hole in my there is a gap in my receive buffer, and that gap is identified with the start of the gap from the beginning. There is an offset of that and the length of the gap. So, that there may be many gaps. So, only those gap information is passed on from his receive buffer, and those are treated as a selective, because we are selecting the gaps, and it is a negative acknowledgement that I do not have this, it is a gap. So, this is how the technique works. So, it requests for retransmission. So, SNAC identifies the MSS sequences that are not received or gaps created in the received MS sequence. Okay. So, multiple segment negative acknowledgement can be sent in a single packet, but it all depends that the SNAC packet is limited by its size with even with extension. So, if there are much more than what it can accommodate, much more gaps are there. So, there will be subsequent NACs will be sent. It specified the offset from the last ACK, offset in terms of number of bytes. Last ACK segment, what was positive ACK segment, and the length of that gap in bytes of the segment that is missing in the receive buffer. Okay. Now, the data receiver actually scans the receive buffer to find out the sequence in to find out the out of sequence queue, and the receiver forms that SNAC option. And there is a specific control field which says that this is a SNAC, and corresponding fields it sent, and along with the normal outgoing ACK segment, it sends that these are the areas which I have not received. You understand this? That is that he has received something and is sending ACK. Earlier TCP standard says that it can send ACK only up to what he has received in order properly. In this case, he has received some segment, and he sending ACK for that segment, and even if there are certain gaps, he will send those gap information. Earlier, he would not have sent the ACK for this, he would have sent the ACK for the up to last one, which is ordered and sequence received, and if there are gaps, he will send duplicate ACKs of that. Instead of duplicate ACK of the previous one, he sends the ACK of the correct one received, and in between which are not received, he is sending. So, that is SNAC. So, SNAC goes along with the outgoing ACK segment, and upon receipt of the SNAC, the sender immediately retransmits all the missing segments as identified by the SNAC option. that is the sender size. So now he knows that these are the though it is in his transmit buffer sequentially they are put, but he knows now in which sequence are missing. So he takes out and puts into is a new queue, and that it's not a standard sliding window arrangement what our earlier TCP we have discussed. It forms a new queue and sends this the missing segments, and of course he tries to fill up the network capacity of that. So the other techniques which are used in this communication are of course that there is a timestamp option, that is the RTT has to be estimated accurately. So for that each along with each segment it gives us timestamp. Normal TCP it sends a timestamp at the beginning of the connection establishment. It sends a timestamp and that goes through different router to the destination, and receiver sends it back. So the sender finds out the difference of the transmit time and receive time of the connection initiation packet, and he estimates that okay, this is my total delay expected, and then he does certain algorithm over that and try to find out what should be the expected RTT and what should be his RTO for a normal packet. But in this case for every packet is sending a timestamp for each segment, and for every packet it knows what is happening to the delay, because the satellite is moving, the probes are moving, or maybe on the ground there is certain movement. So because of that delays will be varying. So therefore the accurate estimation of the RTT continuously is very important. So that is one of the thing which is done. And also we have talked about the window scaling option, which enables the window which is larger than 64 kilobyte size. Then in that case we have given example, with the example we have seen that window scaling option which is required that when RTT is much larger. So these are the various techniques we have talked, and the main thing it's not available always in the textbook. So therefore those who are very much interested to know, I would suggest this way of looking at the references. Though I have listed 4 of them, there are many. So the basic starters, I would suggest that take the reference number 3, which is the TCP IP tutorial and technical overview. It's slightly older issue, but you will know what is generally what is a and particularly chapters. You don't have to read the whole thing because we are looking for the satellite communication part. So read that chapter which is there on internet protocol, that IP, and read the chapter which is on the TCP protocol, transport control protocol. And then you should also read, there is RFC request for these are available in the internet, and that is Internet Engineering Task Force. They issue request for comment with certain numbers and various issues they discuss on that. Some of them are simply informational, some of them are standards. So this is a standard, this is the informational thing where the researches are going on, slightly older. This is but there you will know that what are the issues the TCP people, they were engineering task force were working. So enhancing TCP over satellite channel, this gives you certain overview of the problems what are faced initially and the solution they were suggesting those days, but that is not what fully implemented in what we discussed today. That is available in the first reference. This is a paper which is worked out in detail based on though it is 1997, but based on those days, so whatever TCP standard protocols are were available, and now more or less that is what is running. So what we discussed today is mostly from this paper, and of course they talk in much more detail. I have given you only a very brief tip of the iceberg top thing, and based on their recommendation, the reference first, their recommendation, this the fourth one, which is the standards body CCSDS, which has accepted, and now almost all the space agencies, they are following this the transport protocol standard. Also they have IP protocol standard, many other things are there in CCSDS. So you can go through the CCSDS site also. So with this we stop at this discussion on the higher layer, impact on the higher layer because of the physical layer, and certain mitigation techniques which are proposed and which are being used right now. Thank you very much for your attention.